How do you find the one? Consider the situation in which you need a new pair of running shoes. You go to the shoe store and bypass the dress shoes and the winter boots and head to the wall of running shoes where the shoes are organized by functional type. Track spikes, racing flats, lightweight trainers, neutral trainers, cushion trainers, supportive trainers. Going to the section of the shoe type that you need, you select a few based on their color, their style, their brand, ask for them in your size, and begin trying them on one after another until you get just that right fit, the one that you know will go with you for the next 300 miles. In biochemistry, we call that process a screen, looking at one molecule after another until we find one which has just the right properties. We are interested in finding competitive inhibitors to enzymes, and we do that using a two-pronged approach. The first of those, as is demonstrated by Grace here in the laboratory, is looking for molecules with the enzymes and the substrates in lab. We work in very small volumes with 96 well plates, and using a microtiter plate reader, we can actively test several molecules in one experiment, several in one afternoon. However, in one database of freely available molecules, there are over 14 million chemical compounds which fit into the classification of small molecules that are readily available, aka you can purchase them and have them delivered tomorrow. At that scale, it is a little more challenging to do the experiments in the wet lab, and so we turn to what's known as virtual screening, where we define the active site of an enzyme. That active site then is modeled in the computer, and we begin adding one small molecule after another, testing for its binding energy, making that calculation. As we do that, then the computer can work through one molecule after another, hour after hour, day after day, week after week, and we can find a molecule in a much larger conformational or search space. For example, here I've drawn the active site of one of the enzymes that we're interested in as a ribbon diagram, drawing the residues at the active site, those bits of the protein which are actively involved in the catalysis in their space filling or CPK model. In order to emphasize this rest of the protein structure that isn't drawn, I'll redraw that as a surface, and you can see here that the active site is a deep pocket. We then look through a variety of molecules, one after the other, most of which are poor fits and have low calculated binding energies. But every once in a while, you find the one, that molecule that fills the enzyme active site completely and is a good candidate for looking at more carefully in the laboratory. I'm Kevin Shaw from the Department of Chemistry at Grove City College, and that is how we are looking for the one.